Feedback. So I'll tell you a story about feedback, which dates back to probably early 1900. I think what was happening is that Bell Labs, okay, Bell Labs was involved in developing in setting up the telephone connection, this old age telephone connection from New York to California. This is on the east coast, northeast coast, okay, and this is on the west coast. Okay, 2000 kilometers, 2000 miles or something, this distance. But the distance is not the main problem, because the main problem is that it comes from a very cold climate over here, goes through the desert, Nevada desert over here. I don't know if you heard of this place called Death Valley. Death Valley is the lowest point on Earth. So it goes through the hottest part of, I think, in the US, and then again gets into California through rough terrains and all. So you can see that the weather is changing significantly. Temperature changes significantly. Now, what happens is that when you have a telephone line which travels such a long distance, you have to amplify the signal on the way. So they will have repeaters. We call it repeaters. Okay, repeaters are nothing but amplifiers, okay, which are sitting all along every 5 kilometer, 2 kilometer, or whatever distance. I don't have those exact numbers what was done in those days. Nowadays this is going through optical cable, so you don't need that much repeater. Probably every 100 200 kilometers you can put an optical repeater, and that should suffice. But in the olden days, I think probably every 5 kilometers or 1 kilometer they had to put a repeater. So these repeaters were nothing but amplifiers designed using vacuum tubes. Vacuum tubes. Okay, so you guys don't know how vacuum tubes work. You can look it up, but they also behave in a similar manner like transistors. Okay, they are highly nonlinear. The amount of electron flow is highly temperature dependent. It's all strange. So the characteristics change. Okay, so now what was happening is that they had to in the cold and summer and all, or during rain, they had to keep on changing these. They have to do a lot of maintenance on these repeaters, because they would fail very often. They would not work. So that time, I think Henry Black, he was going to work early in the morning, and he came up with this idea: what if I build a very high gain amplifier and put negative feedback around it and reduce the gain, but the gain is independent of this amplifier characteristic, but is more defined by external passive components like resistors and capacitors. Okay, that is what he said. So resistors and caps do not vary that much with temperature. They have a very low temperature coefficient and they are very stable. So if I can define the gain as a ratio of these two, then it gives you then it is very stable, and then they don't have to worry about doing repeated maintenance. Okay, and all you have to do is design a very high gain amplifier. That's all you have to do. Okay, so he was very excited that he found this result. He went and told his manager. In the meeting, his manager laughed at him, saying that are you a fool? We have been trying to design amplifiers with high gain, and you are telling us that put negative feedback and kill all the gain. So little did he realize that within 2 years, that became the standard all across the world. Okay, it was used in mechanical engineering before, because all these machines and all had it mechanical. But in the electronic circuit, he brought in this revolution. And I think I have a 1920s book written by him. I bought it. It was an ancient book. I still have that one. If you guys are on campus, I can show you that book, because that is my passion, to collect some old, traditional, very old books. It's a very, very old book that I have, which has some of these interesting facts on vacuum, and they have vacuum tube based circuits. So then, so basically, you see that some great ideas, people initially laugh it off and say that this is useless. I'll give you another example, just as an aside, as to how some great ideas. There is a professor in MIT called Robert Gallagher. Robert Gallagher. So I might be getting the spelling wrong. His PhD in 1960. was on LDPC codes in digital communication. I don't know whether you learned or not. It is called lower density parity check codes. Very interesting thing to do error correction. Okay. So what happens is that LDPC codes is a meter sparse code and all. It needs a lot of memory to design something, make it happen. So in 1960, when he did his PhD, it was like people mocked at him and said that, this is useless. Nobody is ever going to use it. I remember in 2001 when I was at Broadcom, and that time we were working in 130 nanometer technology, 19, 20 years back. And that time we were designing memories, and in our group, ours was an R&D group, we realized that LDPC boards could be used. It was not myself, it was my manager who thought, let's build LDPC codes. We have the memories, we'll use those memories to get these LDPC codes. So, and then Broadcom started designing these modems, okay, routers and all these modems which have these LDPC decoders. Okay, I think Broadcom at that time was the pioneer, 2000, early 2000, who thought that this code has makes sense, and they started using it. And later on, I think Qualcomm and all also started using it. But I don't know the exact. It could be Qualcomm also came. I'm just saying Broadcom probably because I think. That is what my knowledge says, but it could be wrong. So I don't want to say it for a fact or say it that. So it took 40 years for this thing to take off, and now most of the receivers, okay, modems receivers have LDPC codes. So what I want to say is that small little things do add up, and don't ever think that any question that you ask is stupid, and don't ever try to mock anybody, because you never know that thing can become that thing can become a practice. Negative feedback is what you are studying right now. In 1920 or something, when he did that, people laughed at him. LDPC code, when he did it, people said that what's the use? Now it is the norm. Okay. So anyway, so that is the history. Now let's get back to our own things. Now two kinds of feedback are there. One is called negative feedback, and we call that as a degenerative feedback. Okay, and positive feedback or regenerative feedback. Okay, now if you see degenerative feedback, the name, it is clear that that's the emitter degeneration that we used, okay, or the source degeneration that we used is a kind of negative feedback. Okay, so it does negative feedback. We did not mention it when we taught it, and because it gives negative feedback, it gives you bias stability. See, any stability comes due to feedback. Our human body has a very efficient means of negative feedback. Now, let me tell you, for example, in summer, you guys start drinking cold drinks. You know what happens when you drink cold drinks? What happens is that the body temperature is regulated at 35 to 37 degrees Celsius or 98 degrees Fahrenheit, 98, 99, it is regulated. As soon as you put in cold water in your body, the body immediately, the negative feedback action in the body kicks in, and it tries to burn more calories inside and generate more heat inside your body to cool down your interior. You feel that, oh, you are feeling good, but inside your body is really working hard to keep you stable. So don't buy this fact that the drinking cold in summer actually helps you. It actually hurts you. You should drink water that is at the temperature of your body. So that is what is the right thing to do. Because otherwise you may get the negative feedback action to kick in and cause problems. Blood pressure is again another classic. Nature has negative feedback built into it. Okay, so that is so negative feedback is there everywhere. Now types of now we will be building amplifiers, and amplifiers could be voltage in, voltage out. Okay, current in, current out. Okay, gain will be AV in the first case, AI in the second case. Then it could be voltage in, current out. Then the gain is transconductance. It could be current in, voltage out. The gain would be called transresistance. Okay, so now keep in mind, AV is the voltage gain is dimensionless. AI is the current gain, which is also dimensionless. GM is the transconductance, Siemens or Mohs, and RM is the transresistance, whose unit is ohms. So please keep these things in mind when you're solving and getting a gain which is different from what it is supposed to be. That means you have done something wrong. So you have to make sure that your gain is dimensionally correct. Okay. So 1 second. Let me put this on the same scale as this one node thing so that my writing area. Okay. So now negative feedback is used to realize amplifiers, any of the above four topologies, so that the following properties are achieved. Okay, so negative feedback will be used to do the following things. Okay, gain desensitization. Okay, make sure that the gain is not sensitive to process, voltage, and temperature. So that is the first thing that negative feedback does. Then negative, what else does it do? It reduces the nonlinearity in the circuit. Make the output linearly proportional to the input. This is very, very important. So this is what negative feedback does. Then improvement in the input output impedances. Okay. Now let us go back to the amplifier topologies. If I have a voltage in, voltage out, what should be the input impedance in this case? If I am sensing a voltage, what should be the impedance? Infinity, right? What should be the output impedance? 0. If I am sensing a current, impedance should be 0. Output impedance should be infinity. Here, it should be infinity. Current out, it should be infinity. Current in, it should be 0. Voltage out, it should be 0. These are the ideal input impedances for these amplifiers. These are the ideal output impedance for these amplifiers. So what negative feedback will do is it will put the feedback, because we cannot achieve these ideal values when I'm building an amplifier. You have seen that. We will get some values. But as soon as you put feedback around that amplifier, then the feedback will make sure that these things approach the ideal values. That means if I put negative feedback in a voltage in, voltage out amplifier, then it will make sure that the input impedance increases from what it was before feedback, and similarly the output impedance decreases from what it was before feedback. And the same goes over here. Am I clear with this? Improvement of the input output impedance. Suppose I have R in as input impedance and R out as input impedance, then of an amplifier. Okay, this is an amplifier input and an output. So one of you please mute, some of you, I can hear some noise. So this is an amplifier. Now this amplifier has an input impedance, this and output impedance. I put negative feedback around this amplifier. Then, and if I'm trying to realize a voltage to voltage amplifier, then this R in is going to increase and R out is going to decrease. This is going to decrease. This is going to increase. This is going to increase. This is going to increase. This is going to reduce, and this is going to reduce. So it is going to, so Rin is going to increase in this case. Rin is going to reduce in this case. This is going to increase and decrease, and same thing with R out. Am I clear? Is that clear to everybody? Does it make sense? Why we use feedback? So it actually, so that is the meaning of, I hope you are clear with the improvement in the input output impedances. Okay, that is the reason it improves the impedances. So the amplifier without feedback is called an open loop amplifier. I'll introduce those terms as we go along. Now it also enhances the bandwidth of the circuit. So if this amplifier has a certain bandwidth, I put feedback around it, the bandwidth increases. Okay, so that is another thing, and it reduces the effect of noise, not discussed and is a little subtle. So this part we won't be discussing. Noise is not part of the syllabus, so we won't be discussing it. It is not that straightforward, but it is a little subtle. So we can ignore this for now. Now positive feedback is used to realize oscillators which serve as clock sources, realize regenerative amplifiers used in latches and sense amplifiers, and find extensive application in memories and digital sequential circuits. Okay, positive feedback is used. So all the goodies of negative feedback come at the expense of reduction in gain. So there is no free lunch in this world. Okay, so please keep that in mind, that all the good things about negative feedback come at this expense, because of which I think Henry Black was mocked at. So that is the thing. So now let's look at the block diagram perspective of the signal flow diagram perspective of negative feedback. So you have a signal source. This could be a voltage source, current source. So accordingly, you will be either sensing the voltage or sensing the current. And the load could be such that either you will be delivering voltage or delivering current. Okay. So this is the amplifier. Okay. This is the amplifier without feedback, and we call that as the open loop amplifier gain. A is called the forward amplifier. Okay. And that is called the open loop gain of the, it's called the open loop gain, open loop amplifier gain. So please keep this in mind. This is a new term we'll be using throughout this. This open loop gain will be AV for a voltage to voltage amplifier, AI for a voltage to current amplifier, current to current amplifier, voltage to current amplifier GM, and RM for a current to voltage amplifier. Okay. Beta is called the feedback factor, the amount of the output parameter, it could be voltage or current, that is taken and fed back to the input, subtracted, is called the feedback factor. This is, so the feedback factor has a direction going this way, and the open loop amplifier gain has a direction in the forward direction. So this is the forward path, forward path, forward path, and this is called the feedback path. So now if we work this out, this is straightforward in this diagram. XO is nothing but A times XI. So we have written that. XF is nothing but beta times XO. And XI is nothing but XS minus XF. So therefore, I can write AF is equal to this. Am I clear? We can write AF given by this expression. Okay. So Xi equal to Xs minus Xf, you can substitute here, and Xf you substitute beta XO and you will get this expression. Okay. So that means the overall gain, now the after feedback, the input and output of the forward amplifier that you have designed is Xi and XO. But once you put feedback around it, the overall amplifier input and output is here and here. So the gain between the overall feedback system. So now this becomes my overall amplifier after I put feedback. This becomes the overall feedback amplifier. So this is the overall feedback amplifier. Okay. So this is the overall feedback amplifier. The overall feedback amplifier gain is defined by the amplifier that you have designed. This amplifier A could be a common source amplifier, common gate amplifier, so then common base amplifier, whatever it is, the one of the amplifier topologies that you have studied, or a differential amplifier as well. Right. Now the beta we will discuss, it is a passive network. Okay, beta is usually a passive network we use, but doesn't mean that it will always be passive. People can use an active network as well here, but we prefer passive network. This is more preferred. Okay, the passive network. So XS is the input, XO is the output. So the overall transfer function of the overall feedback amplifier is a function of, is given by A divided by 1 plus A beta. So we will introduce one more term which is called the loop gain, which is given by A beta. A beta is called the loop gain. Okay. Why is it the loop gain? It is the gain around this loop. Okay. It's a feedback loop. There is no beginning, no end. So the loop gain is A times beta. That's all. Now, typically, we make sure that A times beta is much, much greater than 1. Then the feedback AF is equal to 1 by beta. Now, if beta is determined by passive network, then it is insensitive to whatever variation in A is happening. Okay, but this variation but we have to make sure that the product is much, much greater than 1, then only it becomes. Suppose I have an A which goes from A equal to 100 to A equal to 1000. This is normal practice. If I build an amplifier, this much variation can happen. Okay. Gain variation can happen in the open loop gain of the amplifier. Let's say beta equal to 0.9. then you will see that my closed loop gain AF is called the closed loop gain. Closed loop gain will vary by AF will be equal to how much? 100 divided by 90, right? It is 100 divided by 90, so 10 by 9. Okay, it will be a very small number, so it is going to be 1000 divided by 900. Okay, no, 1000 divided by 900. So you can see that the amount of variation, which is roughly equal to 10 by 9, right? So that means, did I do it right? 100 divided by 90. Yes. So this is again equal to 10 by 9. So you see that after I put feedback, it is roughly the same. It doesn't vary that much. Okay. Any questions on this? And I can design this beta using a ratio of resistors. Okay. Any questions? So AF is called the closed loop gain. AF is called the closed loop gain. If beta is realized using passive circuit, then it does not vary with process voltage and temperature significantly, resulting in stable gain. Okay, so therefore we can say that gain desensitization, if AF, the closed loop gain, is given by the open loop gain divided by the loop gain, and if A changes by 20%, then AF changes by 0.025%, from 20% to 0.025%. And that is how Henry Black was able to save Bell Labs huge amount of money, because the maintenance cost almost vanished. Because the built-in amplifier, left it in the field, let it heat up, let it cool down, it doesn't really matter, because it will heat up and cool down, the gain variation will be 20-30%, or even if it is 100%. As long as we make sure that A beta was much greater than 1, your gain would not vary at all. Can you please work this out and say that if this changes by 20%, AF changes by 0.025%? Can you please work it out? And raise your hands once you are done. In the exam, I have seen question 1, part 1 has 137 answer script, question 1, part 2 has 145 answer script, question 2, part 1 has 132, question 2, part 2 has 127, question 3 has 141, and question 4 has 140. So based on this, I have received highest number of answers for question number 1, part 2, which is 145. Now, if that is the scenario, 145, that means at least 9 people have not taken the exam. Now, if you have not taken the exam, then there is a problem over there. Okay, so let us see. I mean, you will have a tough time passing. Just because it is online doesn't mean that you will pass. In fact, online makes sure that we have much more clarity in the documentation. There is no way, the exam is online, upload is online, database is stored online, it is stored on Google server or stored on Moodle server, dates and timestamps are there. So those of you who have not taken the exam, please pass it on to them that if they do not take the final, there is most likely they are going to fail, because this exam, I think I will put 30%, 25 to 30% weightage. I have to decide on that. 25 to 30% weightage. Okay. The next exam, subjective exam, will have 35 to 45% weightage. I have to decide on that. Okay. So let's say it is 35 and 30, right? So makes it 65. The other three exams that you have taken, that adds up to 35%. And of course, there is an attendance component to it, the attendance, right? So in order to pass, you need to secure at least 1/3 of the marks, that is 30%, 30 marks out of 100 to pass. Okay. So please, those who have not taken this second exam, make sure that you take it. Okay. Take the next one. By the way, did you guys get it? That 20% variation
It will
gives.
depend on A beta, right?
So A beta is always, it is going to be the A beta will be much. So you divided by 1 plus A beta, and then you can write 1.2 A divided by 1 plus 1.2 A beta, right? And put in a value for A. Suppose A equal to 100. Okay. So you should put a value of A, you should get roughly this kind of numbers, right? Okay. So anyway, so this would need some value of beta, but you can show that it will be a very small percentage of variation there. Now the next
So
thing is
1000 A equal to 1000 gives 0.02%.
A equal to 1000. Okay, so let me then craft a problem separately. There is a problem coming up and we'll work that out. Okay, we'll see by how much percentage it changes. Okay, so you can write in a total differential format. Okay, in this manner, we call that A1 plus A beta. This term over here is called the desensitivity factor. 1 plus the loop gain. So we say that 1 plus loop gain is the desensitivity factor. Okay. Now similarly, bandwidth extension. Suppose I have a single pole amplifier. A single pole amplifier is given by this response: mid-band gain divided by the pole location. Okay, where WH is the upper 3 dB cutoff frequency. Okay, that is the upper 3 dB cutoff frequency. Thus, the frequency AF is given by AS divided by 1 plus beta AS, because we know that that is the closed loop gain of the amplifier. Okay, where beta is assumed to be frequency independent, where we have assumed that beta is frequency independent, and because beta is a ratio of two passive components, so it will turn out to be frequency independent. And if you work out the math, you will see that the frequency increases by the loop gain. Okay, 1 plus AM times beta omega h, where AM is the mid-band gain, and so you can see that it increases by the loop gain. The bandwidth of the circuit increases by the loop gain of the overall closed loop amplifier. Okay, so that is the reason why we go for as high a mid-band gain as possible. We might not have this as much high, but ideally we want the gain, DC gain of this is nothing but the DC gain of the amplifier. This is called the DC gain of amplifier, right? This is what you have been amplifier, which is effective GM times effective R out. So we want this gain to be as high as possible. Bandwidth might be lower, but I know that if I put feedback around that amplifier, my amplifier bandwidth will get multiplied and we'll get a larger bandwidth. Okay, so when we are designing an amplifier, we want to make sure that the gain of the amplifier, DC gain of the amplifier, is as large as possible, as high as possible. Now, this one I'll give it as an exercise for all of you. If the open loop amplifier has a lower 3 dB frequency, cutoff frequency of omega L, then after feedback we should get this. You should prove this. So since we assumed a single pole system, the gain bandwidth product is maintained constant. So keep in mind, this gain times bandwidth equal to constant only for one pole system. For multiple system, it is not. So please keep that in mind. This is a misconception lot of them have. Okay, and that is incorrect. So reduction in the nonlinear distortion. So I'll begin that tomorrow. So you can see that the highly nonlinear amplifier is like this, right? So it has really poor linearity. You can see that it is highly nonlinear. But as soon as I put feedback, it almost becomes like a linear amplifier, almost a straight line. So the feedback converts this nonlinear characteristic into a linear characteristic and improves the nonlinearity significantly. Okay, so we'll discuss that tomorrow, and that's where you can analyze the sensitivity, because we are giving you the gain numbers and all. And then the enhancement of input-output impedance. We'll discuss this. I have to spend quite a lot of time because this has to be done at the block level, and then we'll go into the transistor level aspect. Okay, so any questions?